So, carrying on our discussion about projectile motion, let's discuss a question where what if we want to know the launch speed for which some angle results in the same maximum height? And for example, we could say, well, 10 meters. So let's say we have three illustrative cases where we've got a angle of 75 degrees, an angle of 45 degrees, and an angle of 30 degrees, and we're going to color code them. Okay, well, we know that there's going to be a relationship between the angle and the maximum height. If they all had the same launch speed, we're going to have a largest maximum height for whatever has the largest angle. So that'll be the 75 degrees case, because most of that launch speed will be in the y direction, giving us that maximum height. So let's say the 75 degree case gives us a maximum height of 10 meters. And we want to know, okay, well, what launch speed will then enable me to reach that same height at 45 degrees or at 30 degrees? And we know, and I'm going to write this down as a little note here, because we know that as we have a smaller angle, we're going to need a larger launch speed to get up to that same height. So I just made a note of what these example angles are for 75, 45, 30. So let's just say, well, let's just note from the beginning that we expect the launch speed needs to be greater for smaller theta, because the maximum height depends on the Vy, and that is equal to V sine theta. And that sine theta, remember, is maximum at theta is equal to 90 degrees. And so the larger that angle, the easier it will be to get to some height. Okay, so let's take a look. First of all, we have an equation for the maximum height in terms of velocity, angle, and g, the acceleration due to gravity. And for this work, we're going to define that as negative 9.81 meters per second squared. Previously, we've looked at this and already did that work. I'm just going to go back to the old work. I'm going to copy it all and bring it down. Copy. And into the box. Okay, so just a quick recap. What we did there was we set up a kinematic equation where we had the final velocity squared is equal to the initial velocity squared plus 2 acceleration delta y. And we said, well, we know when looking at the max height that at that peak point, if you're just looking at the initial to the final, well, at that peak point, that's going to be 0. And so we rearrange this in terms of height. But what we want to do in this case is to, in fact, look at that equation but isolate the velocity so that we understand how the launch velocity will be related to these other terms, the h value, the theta. And so let's pull this out over here and let's do that. So first of all, we'll take the denominator, the negative 2g, pull that out to the side and say negative 2g h is equal to v squared sine theta squared. and then just flip the sign. So v squared will be equal to negative 2gh, and we're going to pull that sine theta squared down into the denominator. Okay, now we need to get that square out, so we're going to take the square root of both sides to get v. Now the square root will take care of that sine squared term, no more square. So let's just write that. So now we just have the sine theta term, but we're going to be left with this square root up on the negative 2gh. Now, don't panic about the negative, because remember that g value is negative 9.81 meters per second squared. So we'll in fact end up with a positive value under the square root. Okay, so let's just, because that's important, draw a little box around it, because that's our equation now for the launch velocity in terms of g, which is not going to change, angle, which is going to change, and we've got a target height. So now what we're going to do is, for each one of these cases where we've got an angle and we've got a target of 10 meters, let's find out what the launch speed needs to be. Okay, so to do that, what I'm going to do is I'm going to just copy this. So I'm going to duplicate, and we're going to do this 3 times. So this will be 1. This will be 2. And this will be 3. And we're going to color code our cases for each of these angles. Blue. Okay. Okay. So in the case of the orange, we've got a launch speed is equal to negative 9.81 meters per second squared, and we're going up to 10 meters. Oh, put the negative in there, yeah. Okay. And that was because g had the negative, so that was cancelled. And then sine, that's the case where we've got 75 degrees. Okay, so what is our launch velocity there? 14 meters per second. Okay, good start. Now let's go over to the case 2, where we've got 2 negatives, so that's going to cancel out the negative. 9.81 meters per second squared, up to our 10 meter height objective, all under the root. And then we're going to have sine 45 degrees in that case. I don't like that root. I'm going to draw it again. A little better. Okay, so we get a velocity now. We plug in those values. We get 20. So we get 20 meters per second. And final case, okay, so we've got our velocity is going to be equal to, we've got the 2, negative 9.81 meters per second. The negatives cancel. Our 10 meters the root, and we've got sine 30 in this case. Okay, so here we've got a launch speed of 28 meters per second. Okay, so now we're starting to see the relationship here between the launch speed and the height. So when we have an angle where we have an angle of 75 degrees, we can reach that height of 10 meters with only 14 meters per second. But as our angle gets smaller, we need more and more velocity to reach that height. And one thing that we can do here is to understand this a little bit more clearly, and I think that this will be very informative. And so I'm just going to draw a line here. This will be really significant. Well, let's consider just the y component in each of these cases. So what is the Vy in this case? Well, that's V sine theta. And so that theta here, okay, so it'll be V, y is going to be 14 meters per second sine 75. So our Vy is equal to 14 meters per second. Okay, so just a quick comment about rounding. I'm keeping 2 digits just to be consistent with the fact that I'm looking at 10 meters. That's 2. You know, if you were a little bit more precise, you'd see that there is a small amount in the x, but it rounds to 14. Okay, so let's carry on. Let's look at the Vy in the second case. So that's, you know, your V sine theta again. Your Vy is equal to 20 meters per second times your sine, in this case 45 degrees, and so our Vy is then equal to 14 meters per second. Well, what about a third case here? Let's do this one more time. So your Vy, V sine theta, Vy is equal to, in this case, 28 meters per second sine 30. Our Vy is equal to 14 meters per second. Isn't that rather interesting? So in all of these cases, to reach that same height, we all had the same Vy. Now, to convince ourselves that this is all true and consistent with our conceptual understanding of what's going on, I'd like to go back to that equation where we talked about, okay, we have an equation for the V related to these two, ignoring gravity is the kind of constant, to these quantities of height and angle. So we had this equation. Now, what I'd like to do, and that was a little messy, I'm going to just copy it from above. Let's copy it here. I'm just going to pull that down, and we're just going to interrogate this a little bit. And in fact, I'm going to duplicate. I'm going to pull it over here, and this is what we're going to do. I'm going to multiply both sides by sine theta. So I'm going to multiply both sine theta here, and I'm just going to move this over sine theta here. Okay. Just going to draw a little box around this. Keep it separate. Okay. And so why did I do that? Well, I want to do that to cancel this term. Okay. So I'm canceling those two sine terms. And so by doing that, I can then rewrite this in an interesting way. So now it's just going to be equal to square root -2 GH. And what is this? That is Vy, right? So that's our Vy. So now, okay, we've just got an expression for the y component in our velocity is equal to this. Okay, fine. why is that interesting? Why is that informative? And why is it related to this reveal that we've got the same y component of the velocity for each, no matter what angle we're looking at, if we're reaching the same height? Well, what's interesting here is that this is the same as the delta y in the 1D case, in the one-dimensional case, where we throw an object up, straight up, where we throw an object straight up. Well, just to kind of bring this point home a little bit, like let's draw that. So I mean, if you have some object at this initial position, and then you, let's get the dash line, throw it up. Maybe I'll gray that. Okay, and we throw it up to some other height here, and that we're going to call our final position. Okay, so this will be our final. That's just throwing it up in the air, some height. Okay, so we could say some height. Well, how do we look at that? What you can do is v final squared is equal to v initial squared plus 2a, in this case g, delta y. And we know that this final velocity is 0, because that's, by definition, you throw it in the air, and when it is at the maximum height, it's gonna stop. Okay, and so then we've got 0 is equal to vi squared plus 2g delta y, and then we're just going to isolate for our vi. So let's bring the vi squared over. So now we've got negative g delta y, and then we have to take the square root. So we've got vi is equal to the square root of negative 2g delta y. And there we now have related the initial velocity of that object we just throw straight up in the air to g and to delta y, or if we want, to h, because we called it h. Maybe I'll do that here. And that is the same expression that we got for here. So this is really interesting to remind us that when we're talking about projectile motion, and we go right back to the very beginning of this earlier discussion, that the x and the y motions are independent in projectile motion. They're linked by time, but what's going on in the y direction, we've got this acceleration due to gravity, and it is identical to the 1D motion of an object thrown straight up. And we saw that working through all of these examples and this detail and this really interesting, informative question where we work out, well, what kind of velocity do we need to reach the same height, at these different angles? Well, we may need different velocities, but that's because ultimately what we need is the same y component of the velocity. And the impact that change in angle is simply what proportion of that is going into the y to give us that number that we need. So if we need that 10 meters of height, well, that tells us we actually need our 14 meters per second in the y direction. And we see how that's related then to the case where it's one-dimensional and we're just throwing the ball or the object up into the air. Okay, that's it.